So the idea is this: whenever we build machine learning models, so we always have some kind of assumptions built into the models, because whatever model you're going to put together, there's always some assumption, some bias associated with these models. And what we are interested in knowing is this: how can we kind of extend those models learned based on the observed data, based on your training data, to unobserved examples? And then that would be some of the classical concept of interpolate, extrapolate. That would be very useful. Essentially, I want to interpolate this kind of observation from this known collection of data sets here to something unknown, or extrapolate, right? So if the data is located outside the range of the data you have, can you extrapolate them? And so what kind of functions should we expect to try to learn those fit to the observations? And what usually we have some bias kind of built into your models. And sometimes we call this type of bias called assumptions, right? And whenever you put together a model, and you immediately put together assumption on your models. So usually what happens is that we should always only allow data to kind of pull us away from the assumptions, only with this evidence. We start with assumptions, but then with data, we might be deviated from the assumption a little bit, and that's okay. But we only should allow data, allow us to do that, learn from the data itself. So this is, for example, this is the case here. Suppose this is the observations we have. And imagine this is something like a regression problem. You want to learn the relationship between y-axis and the x-axis here. And you have a few samples here that was shown up in this plot here. And then the question you ask you here, I want to learn the relationship between y and x. And then hopefully, after I learn the relationship here, I can make predictions. And the prediction could be interpolate. For instance, if I have data located in between here, I want to know the values, the y values of this particular data sets here. Suppose I have one here, I want to learn what's the values of this ones here, and then interpolate might be say what something in between here. And then extrapolate, say if I have something outside the range of the x here, and what will be the values of corresponding this x here? Is this going to be here or here or here, right? So that is the question the core question that machine learning is trying to answer. So well, to answer that question, you always need to build some bias, make some assumptions. So one assumption might be you want to make here, they say, I'm going to assume the relationship between this y and x is a linear relationship here. And that's the assumption you're going to have, right? And then, you have some of the degree of freedom associated with this linear assumption. That would be the slope of this curve and the intercept of this curve here. And that would be 2 degrees of freedom. You can change and to make your kind of model fit to the data sets. And that is how learning is doing. Learning try to identify the best slope and best intercept such that the data somewhat match the observations here. And that will be shown in this kind of curves here. All right, so this is one type of assumption. The bias, right? So, but here is that I'm going to assume the model is a linear model. Of course, and you can make other assumptions. You can make the model less biased. I'm saying that, well, I can say not only I'm going to allow model to be linear, I allow it to be kind of slightly quadratic functions of that. So this kind of model is certainly more complex than the linear models, and correspondingly, the number of parameters associated with this new models is larger than the number of parameters associated with this initially the linear models. So I can still kind of fit the parameters of the model based on the observations I have here. And in that case, the best fitting I identify is this lines here. So this is a new kind of model I have, and based on my assumption that the model here is kind of quadratic functions of that. Of course, you can go even beyond that, say, well, I can even tolerate more degrees of changes, and I allow to have a higher order polynomial functions as my underlying models. So in this case here, you still have a bias. Your bias is less strict than the initial bias of linear or quadratic model, but it's still a bias. You have to assume certain degrees of polynomial functions and for your underlying models of that. And you might say, I want to assume this is the 7th degree polynomial functions, and then that's my underlying models. Well, and then you can still try to fit the model to the underlying observations here and identify the models here. And that's what will be the fit of the underlying observations. And this is all good. And based on this observation, you can see that, and when your model is more complex, which means there's more degrees of freedom, it's richer models. Because in this kind of example that I give here, so linear model is a subset of this kind of quadratic functions. And then this quadratic function is a subset of this kind of same order polynomial functions. So you can see the model space become bigger and bigger. As a result of that, the fitting to the observation becomes better as well, right? You can see that this kind of blue line fit better to the observation almost perfectly than the other models, right? So what the question is this, right? How do we know? Should we determine that this blue model is better than the red or green models? And that's the key questions always in our mind. What's the best model? Should we choose, right? So it turns out that what we interested in, we care about is not how model fit to the observations. Instead, we're trying to answer these questions here. I want to see how to extend those observed data to unobserved examples. And that's something we call the testing data. We care more about the performance of the model, prediction performance of the model on the unobserved examples and the so-called test data sets of that. And then, so for that type of testing here, it's not clear which model is better. Certainly depends on the type of data is provided to you. And for instance, if your actual test data, the true model look like this one here, it's not clear which model is better in this case here. You might actually prefer the linear model is a better model for this type of data than the other models, right? So this is a kind of key idea behind machine learning is that whenever you build a models here, there's always underlying assumption you're going to put onto your models. And the question you should always check to verify whether the assumption is a good assumption, is a reasonable assumption, or maybe is a too strict assumptions of that.